Hello, my name's Jeff Messier. I'm a professor in electrical and software engineering in the Schulich School of Engineering. And in this video, I'm going to be introducing you to the hands-on lab exercises in the ILS edition of ENCM369. And so what I'm going to do is I'm going to start out with just some general comments that are going to help you for all of the lab exercises. And then in the second part of this video, I'm going to dive in and do a little bit of a demo video to show you how to do the first part of lab 1. So a couple of things, or I guess the first thing I'd like to do is lay out my learning objectives for these labs. And sometimes it's maybe, especially when you first get into engineering, a little bit different it's a little bit hard to see the differences between the different engineering disciplines. And in particular, sometimes the difference between software and electrical engineering is a little blurred because software engineers program a lot, electrical engineers program a lot. But one of the key and very special things about being specifically an electrical engineer is you learn how to create what are known as mixed signal designs. And this means you learn how to create a design that contains both digital elements like logic, microcontrollers, as well as analog kind of continuous signal elements, things like microphones and sensors and speakers and stuff like that. And working with both digital and analog in the same design is something that is unique to electrical engineering and is one of the things that we're going to focus on learning how to do in 369. So the goal of 369 is to introduce you to something called embedded design. And embedded design might be sort of a catchphrase that you've heard already. And it basically refers to taking some kind of microcontroller or digital processor and embedding it into a larger design. So for example, the car or the computer in your car is an example of an embedded design. So that's where the designers at the car company have taken a computer and embedded it into a larger system, which is basically all of the control apparatus of the automobile. And embedded design and mixed signal design is just everywhere. So cars are a good example. Smartwatches are another good example. There's obviously a processor in a smartwatch, but it's connected to all kinds of sensors, even to a certain extent, smartphones. Although once you start to get into a system that basically consists of a processor, some memory, a screen, and then some peripherals, you're sort of getting into the realm of kind of computer design, laptop design, smartphone design. And we typically don't refer to that so much as embedded design anymore. Embedded design is typically non-smartphone, non-computer type designs. And so when I think about what I'm going to teach you in 369, a big part of what we're going to be learning about in the lectures is basically how to build a microcontroller from digital logic. And this is basically what designers at Intel, AMD, NVIDIA, Apple, ARM, all of these big sort of microprocessor design companies, they have hosts of engineers who are focused on building microprocessors on silicon chips using digital logic. Super interesting jobs to get, but relatively rare in the big scheme of things. So if you were to go on to get that type of job, typically you would take some sort of computer engineering type master's degree or PhD, and then maybe go to maybe Eastern Canada, Silicon Valley, kind of places like that. Although these jobs are starting to spread to other centers, they're relatively rare. However, what's much more common is being an an electrical engineer working at a company and then needing to develop a design where you want to plunk down a little microcontroller to add some intelligence to your design. So for example, a smart agriculture company, you would like to use a microcontroller to monitor soil moisture levels and sunlight levels. A solar panel company might use a microcontroller to control the tilt of the solar panels. Microcontrollers are used everywhere for oil and gas instrumentation. So there's a bunch of companies, basically almost everywhere you have engineering that is making some kind of an electrical engineering product, a microcontroller is typically involved. And so the skills that we're going to be learning specifically in the labs and the hands-on exercises, I believe are very marketable, and your chance of applying them in the workplace is actually pretty high. So the other thing that I wanted to talk about, and this is new for this year, is that the labs, as much as we can manage them, will be individual. So in order to do the labs, you will need access to, or ideally you will have access to a laptop with a USB port. And if you have access to a laptop with a USB port, and obviously all laptops have USB ports, you can download the microcontroller programming environment, and you can do all of your development on your laptop, and you can just hook the microcontroller programmer into your laptop. However, if you don't have access to a laptop that you can use for the labs, let me know, and then we will look at allowing some groups of people to work in partners, or the department also has a limited number of departmental laptops that we can sign out to students for use in the lab. But if you do have access to a laptop that you're used to working with, that's by far the preferable route to go. So we're going to do individual labs as long as you're able to work on your own and you have access to a laptop that works. If you don't, please reach out to me, send me an email directly, let me know, and we can look at other arrangements. So practically speaking, because of logistics, there might be a few students working in groups, but we'll just sort of navigate that as the term kind of develops. So invariably every year I hear at least a few students referring to these as programming labs. The 369 labs are not programming labs, or not just programming labs. So to clarify that, you definitely will be writing some C code for our labs. So C is the programming language that we're going to be using. So you've taken 335, and so we're going to use those skills. We're going to put those skills to use. But this isn't a programming class like 335 was a programming class. These labs are basically what you're learning in the 369 labs is how to use software to control the peripherals of the AVR microcontroller. And basically, we're going to use software to control how the AVR reads in external digital and analog signals and generates analog and digital signals for output. And so every single one of these labs, we're not just going to be writing C code, we're going to be generating signals and feeding them in to the AVR to see if the AVR can understand the signals we're sending it. We're going to use the AVR to generate signals, and we're going to look at those signals on our oscilloscopes to make sure the AVR is working properly. And so the labs are much bigger than just programming like you would have been doing in your programming classes to date. The good news is that most of your programs are going to be very short. We're not writing hundreds and hundreds of lines of code in 369. Typically, kind of 20 lines or less. So you might be thinking, wow, I can write 20 lines of code in a heartbeat. Well, this is where you get some insight into what it's like to be an embedded designer. Embedded design is typically done on relatively simple microcontrollers like we're going to be using in 369. But designers have to put a huge amount of thought into basically each line of code that they write on the microcontroller. And that means the datasheet, the AVR datasheet, is going to be hugely important. It's not an exaggeration to say that you are going to be reading the AVR microcontroller datasheet. You're going to spend way more time reading that datasheet than you are actually writing code, because the biggest part of these labs is learning about all of the complexities and the features and capabilities that the AVR has to offer, how to control all those features using software. And once you have all that knowledge, then you write the program to solve the particular problem that I'm asking you to do in the lab. And this is pretty representative of actual embedded design in industry. So, embedded designers in industry don't write, hundreds of thousands of lines of code. Most applications, like automobile applications, even though some of these are starting to get fairly big, but compared to, games or web applications or, office applications or a lot of apps that run on smartphones, embedded programs tend to be fairly short. And so, as I said, the datasheet is absolutely the key. There is no way you can succeed in the 369 labs without having an absolutely intimate knowledge of the datasheet and its contents. There's no textbook for 369, but this datasheet, you're going to read it as much or more than you normally read a textbook in your other classes. So it takes a long time to get used to a datasheet. So when you open up the datasheet for the first time, you're going to see it's hundreds of pages long. And I don't expect you to read it from the very beginning to the very end. In fact, one of the skills I want you to develop in 369 is to learn how to read a datasheet. And the way you learn how to read a datasheet is to sort of scan, kind of the introductory contents, the table of contents, get an idea of what's in the document, and then know specifically what sections to dive into for the particular problem that you're trying to solve. So I'm going to give you a hand with this. I'm going to give you a pre-read for each one of the labs. So in advance of each lab, if you look at the lab handouts, I'm going to tell you which sections of the datasheet to look at, and basically dive into those sections and read those sections. When you use the AVR application for, or the AVR microcontroller for other applications, again, being able to skim over the data sheet, identify the sections that you need, and dive into those is a really key skill. So just a few words about the particular microcontroller device that we're going to be using in 369 this year. I've chosen the AVR 128DB28 microcontroller. And so the AVR refers to the family of microcontrollers. 128 is basically the model number, and 28 refers to the number of pins. So the actual physical devices are going to be DIP packages with 28 pins, and we're going to put those, squish that package into a breadboard and start hooking up signals and wires to it. So we're going to be using this particular microcontroller for all of the lab exercises. You're also most likely going to be using it for your ENCM369 design project as well, because you're going to need to make a prototype of your design. So you're not, this year you're not absolutely required to use the microcontroller, but most of you likely will choose to use it just because I think it makes sense and it gives you a lot of design freedom. And we're going to support myself and the TAs for ENCM369. We will support you in your ENEL300 design projects as well, answering technical questions about the AVR, what it can do and what it can't do. The reason why I chose this particular chip for 369, first of all, is that it's a pretty modern chip. It's from the same family of microcontrollers that are used in the Arduinos. And a lot of you, not everyone, but a lot of you will be aware of Arduinos. You might have maybe done a project with them in high school maybe, or a summer camp or something like that. And so It's a fairly mainstream family of microcontrollers, and this particular version of the microcontroller family is extremely versatile. It has a huge number of features. It's actually a way better chip than the chip that's used in a lot of the Arduino boards, particularly the Uno board. It's got an analog to digital converter, a digital to analog converter, a whole bunch of comparators. It's just a very flexible, cool chip that's really, really good for any kind of low power sort of embedded design. That said, the device does have some limitations. So in previous years, there's been a few groups in ENEL300 that said, oh, we're going to use the AVR chip for voice recognition, or we're going to take Fourier transforms, which is something you learn about in 327, or we're going to use, I think even one group was thinking about using image recognition or hooking up a camera to the AVR. And these types of things are way beyond the capacity of the chip. It's a small, very simple little chip. It would be a perfect kind of chip for sort of a wearable type design. It uses very little power. It can hook up to a variety of sensors and some simple display elements, but it's not gonna do the kinds of things that your laptop can do, for example. So just really, when you're scoping out your ENEL300 design project, be really careful about choosing a design that is within the capabilities of the AVR chip, if that's what you want to use. And if you have questions about what the AVR chip can or can't do, there is an ENEL300 discussion forum on the 369 D2L page, and you can post those questions there, and I'll help you out. Another thing that I want to emphasize is that you won't have access to a whole bunch of pre-written libraries that you can use with the AVR. So for example, Arduino boards are pretty famous for having this whole host of peripherals, all these displays and wireless chips and all this kind of stuff that you just plug into the existing Arduino board, and then there's a library you can download, and then you can use all these peripherals. None of that exists for the AVR. And in fact, 369 is really the class where you would learn how to write those libraries, right? So somebody went to all the work of writing the libraries to do the low-level interfacing with a particular peripheral. That's basically what you're learning in this class. So there's no libraries available, but you would basically write the code that would replicate the functionality, perhaps, in some of those libraries. So in this slide, I'm going to introduce the concept of what are known as special function registers, or SFRs. And I'll come back to this idea when I'm introducing Lab 1. But on the previous slide, I said, okay, the whole point of these labs is to learn how to use software to control the peripherals of the AVR chip. And you're like, okay, great. How exactly do I do that? Well, basically you do that by reading and writing, by writing to and reading from special function registers, or SFRs. So what this looks like in your C program is basically copying values into specially named variables, or reading values out of specially named variables. Specifically, SFRs are represented by specially named variables, and I'll give you a few examples of what this looks like. And if you want to write a value into a special function register, then you copy a number into the special variable in your C program. And if you want to read a value from the special function register, you copy a value out of the specially named variable in your C program. So for example, one of the things that I'm going to show you how to do shortly is to configure some of the pins on the microcontroller to be digital output pins. And the microcontroller is very flexible, so its pins can either be digital output pins or digital input pins, and you need to tell the chip what you want to use each pin for. And you do that by writing a 1 or a 0 to a special register. So you write a 1 to a particular register called the dir set special function register if you want to use a particular pin as an output. And there's going to be a variable in the C function called dirset that will just copy a number to, and that's going to configure the functionality of the chip. If you want to see a listing of all the special function register variables you have available to you, I've posted the IO AVR 128db28.h include file on D2L. You do not have to specifically include this in any of your programs. This is done automatically inside the development environment. It's just useful to have access to this file because then you can sort of do just a lookup for all the special variable names that match these function registers. And like I said, I'm going to work through an example here in a minute, and this is going to make a lot more sense. Just a quick word about the development environment. So the development environment is called MPLabX, and it's free, which is great for 8-bit microcontrollers, which is what we're using in 369. And it runs well on all the three major operating systems. And I've got a special document posted on D2L with the instructions of how to download and install this development environment on your laptop. And in addition to installing the software, you're going to need a USB port that can plug into what's called a snap programmer, which is a small printed circuit board that we use to connect to the microcontroller to program it, to feed our program into the microcontroller. And you need a regular USB port for that. So it doesn't have, it can't connect to a USB-C, for example. So you'll need a USB-C to USB adapter, which probably most of you have. And if you don't, we do have a limited number of them that can be signed out of the lab, but ideally you'll have one of these because they're pretty handy. All right, now I'd like to say a few words about interconnect. So interconnect is a special engineering word used to refer to wires. So the interconnect in your circuit is basically all the wires you have connecting all of your components together. And it is no exaggeration to say that the vast majority of problems that you're going to have in your 369 labs are due to interconnect. Basically, wires that are too loose, wires that are accidentally plugged into the wrong pin on the AVR controller, wires that are connected to nothing, wires that stick out of your board so that when you bump them, they become disconnected. And this carries through to real engineering. So when I worked in industry, I had a whole job for a while just taking care of all of the special cables that were used to connect various equipment modules together, and making sure you've got the right cables that don't wear out. It's a huge thing. And so here's a couple of tips that you absolutely have to follow when you're doing these labs. First of all, keep your breadboard neat. So in particular, use very short wires. Here's a picture of a great example of an amazing breadboard. So we have a bunch of components here. Here's a connector to the 5-volt power supply. Here's a DC conversion component. We're not using that this year. But take a look at these excellent little wires. They're, it's important to, for this particular circuit, the designer needed to connect a bunch of traces together, and they use the shortest possible connections. This is great for a couple of reasons. First of all, it's very easy to debug. When you've got a big long wire that sort of starts and then it snakes out and then it plugs into another spot in the circuit, you have no idea which wire is connected where. And like I said, as soon as you've got large nests of wires, you can brush them, they'll become accidentally disconnected. And this is not such a big deal for our circuits because we're relatively low speed. But when you start to do higher speed digital design, long wires like this can cause you problems by making your signals really noisy. And so use short wires. You'll be working with a 5-volt wall supply. It can easily pop out of your board. So use an elastic band or zip ties or a piece of tape if you have them to sort of tie down the little connector where your power plugs into your breadboard. That's basically what this particular person has done here. This is the adapter for your power. It plugs right into your board. And this particular person used an elastic band to hold it down. Again, just so like if you bump things, your power can accidentally come unplugged, and then your whole circuit doesn't work. And make sure you trace your voltage levels all the way through the circuit. So don't just assume that you've connected your power properly. Make sure that you use your multimeter to make sure you've got the exact proper power levels at exactly the right pins on your microcontroller, right? And because even if you miss and you just plug your power in one pin over, your circuit's not going to work. And you're going to work with this, and sometimes this can be a little frustrating, right? You're like, oh, I just plugged it in, I had it backwards, or I just plugged it in the wrong place. But this is really what this kind of design is all about. So the 369 labs are really, like, to succeed, it's all about just being careful, methodical. Don't go fast. We're going to give you lots of time to do these exercises. Just make sure you go step by step by step. As soon as you start to rush or take shortcuts, that's when problems can happen. Okay, so how do we get help? Or how do you get help, right? And please, expect to need help. This is, not something that you're just automatically going to know how to do. This is tricky, and it's a really big, important, brand new skill set to be able to effectively program these microcontrollers and use them in a circuit. So you're going to basically be working on this, working on the hands-on exercises in two sort of settings. The first one will be during the studio sessions, right? So every week, every Thursday morning, we have a studio session. We're going to start the studio session, usually approximately the first hour, talking about theory and assignments and the questions from the videos. And then we're going to use the last 2 hours to basically just allow you to work on the hands-on exercises. We may also open up some Friday afternoon sessions as well, but we'll just sort of see if those are needed or not. And you have trouble, put up your hand, and one of the TAs or myself will come around and help you. However, we will not answer questions like, what's wrong with my circuit? Or, hey, TA, fix this problem. We want to make sure that you are making an effort to engage in active problem solving. And so the very first thing that we're going to ask you, always, the very first question is, what steps have you already taken to troubleshoot your problem? And basically what we want to find out is we want to get you to tell us what you know for sure is working, right? So let's say, for example, your programmer is timing out with an error, right? And the error is, there is literally like a timeout error. And we might ask you something like, oh, well, is the power properly hooked up to your chip? And you're like, well, I'm not sure. Okay, well, why don't you take your multimeter and check to make sure that 5 volts is present at all the pins where there should be 5 volts. What about your ground pins? Are they hooked up to ground? Yeah, they are. Okay, well, great. So it's probably not power. What about the wire that runs from the programming pin to the programmer? What's that one like? Oh, it's pretty long and snaky. Oh, well, okay, well, yeah, I can move it a little bit. Let's try a shorter wire. Hey, that fixed the problem. So, and there's a lot of students, so there's going to be a lot of students to help, and there's only so many TAs. And so we're not going to sort of necessarily stand around and watch you while you do all of this troubleshooting. So if, for example, I come along and I say, hey, have you checked the power on your chip? And you're like, oh, no, I haven't. Then I'm not going to hang around and wait for that, right? I'm going to let you check the power on your chip. and I'm going to move around and help somebody else while you do that. And then you put up your hand if you're still having problems. So if you want to make sure that, the TA or myself is focusing on what is probably really the problem, make sure you rule out those really kind of more obvious things first. The other place that you're going to be working on the hands-on exercises is outside of the studio sessions. So you have access to the ILS room and the equipment anytime. You will be signing out the programmers and the breadboards and the chips and the ADALM USB oscilloscope. So really you can work on this anytime, and probably you will choose to work on it outside of the studio sessions. Every lab you'll have basically 4 hours of studio time to work on the lab exercises, and that's, as long as you're doing your pre-reading and you come prepared, that should be enough. But you might find that you do need to work on it a little bit outside of class as well, and that's totally fine. If you do and you need help, basically, like everything in 369, post on the appropriate D to L forum. There's going to be forums for labs 1, 2, and 3. And make sure you post in the appropriate place. And when you do help us out, be very descriptive. Post screenshots. Tell us what you've already troubleshooted. Say, I've checked the power. It's definitely not the power. I've checked the connections. They're all nice and tight and small. Then that helps us, get around to your problem. And like I said before, if you are having trouble and it's specific to your ENCM369 design prototype, there's a separate discussion forum for that. And I will be answering questions there as well. But make sure you put all of your questions in the proper forum.